Now that we've learned that the force of friction is a property of the material, the surfaces, and the force that the surface applies to the object. So if here is our box, and here is the surface it's sitting on, there is an interaction between the surface and the box, and this interaction here, as these two surfaces rub past each other, creates a particular kind of resistance, and the symbol mu is used as the coefficient of friction. Let's say this box has a mass of m, and we are going to pull on it to the right with a cord. Okay, and so you are pulling on this box with this cord, and you are pulling it to the right, and as you pull on it to the right, the box maybe doesn't move, and so you have to pull on it with a bigger and bigger force until it finally moves. And that is the difference in the static friction force and the kinetic friction force. So we can describe the force of friction static as being equal to or less than the coefficient of static friction times the normal force. We can describe the force of friction kinetic meaning moving, as being equal to the coefficient of kinetic friction, I'm using a little k here for the word kinetic, times the normal force. So the static coefficient is always greater than the kinetic coefficient. And remember, static means not moving, while kinetic means moving. And so this coefficient will be some number, usually less than 1, always less than 1 for the coefficient of kinetic friction. So let's go back to our example with our person pulling on the box. Let's say, for example, that the coefficient of static friction between the box and the surface is 0.3, and the coefficient of kinetic friction is 0.1. What force would we need to pull on the cord with in order to get the box to just slip? First, we start with a free body diagram. We're going to start by drawing a free body diagram of all the forces acting on the box. So here is my box. We are pulling on it to the right with a force and a cord, which I'm going to call the force tension. There's also the earth pulling on the box with a force F sub g for the gravitational force. There's also a force on the box straight up from the surface. Remember, over here we've got the surface, and the surface is going to push up on our box. So over here on my diagram, I'm going to draw a force normal. Normal being from a surface. So it has to be from the surface. And then because the surface is rough, there is a friction force. Force friction. Now, just to get the box to move, so that means it's not moving. Not moving would be static. So I'm looking for what is this maximum tension just to get the box to move. So now that I have drawn my free body diagram, my next step is to sum the forces. So I'm going to sum up, remember sigma means summation, the forces in the x direction. And they should be balanced in equilibrium. So we'll have force tension to the right minus the force friction static to the left equals 0. So I'm just looking at these forces in the x direction, and I'm writing them down, and I'm using the direction of the arrow to get my sign. So this was plus, this one is minus because of the force to the left. Now let's sum the forces in the y direction, that's up and down, and they're also going to be balanced, and those forces then would be, let's get a little more room, the normal force, which is straight up, minus the weight, and that's equal to 0. Now I'm looking for, the question is asking me what force is needed to get the box to move. So I want to find the tension force. That's what I want to find. And this is the tension force right here. So if I do a little algebra here, then the tension force would be equal to the force friction static. I just added this over to the right side there. Now the force friction static, that's an equation. That's an equation that we've learned already. And so if I substitute in that force friction static equation, which is mu sub s times force normal, I'm a little bit closer to solving for the tension, which is what I want to find. Remember, we're still looking for this tension here. Now I have the coefficient of static friction way up here, and I don't know what this normal force is, but I do see that here in this equation there is a normal force, and so I can do the same sort of thing here with my algebra and say force normal is equal to Fg. That would be the gravitational force. Again, I just added Fg to both sides. So this means that F normal is equal to m times g. Remember, the gravitational force is equal to the mass of the object times the gravitational field. So now I can do another step of substitution where the force tension is equal to the coefficient of static friction times force normal, which is equal to mg. So I'm going to make that substitution here. So m times g. And then all I need is the coefficient, the mass, and the gravitational field. So if we go back up to our problem, we can see the mass of the box is 20 kilograms, and the coefficient of static friction is this 0.3 given there. So now I can take those numbers and substitute them back in. Down here. So now the force tension would be equal to 0.3 times 20 kilograms times 10, which should be 60 newtons. Remember, Newton is the unit for force. So now, what if I want to pull on the same box, but I want to pull on it at a constant speed? So right now I know in order just for me to get the box to go, I need to apply a force tension, has to be greater than or equal to 60 newtons to get it to move, to get it going. So now, what force do we need to apply in the cord to keep it going? So now the first thing I need to do, like all problems, is draw a free body diagram. So I'm going to draw a box to represent the box that we're trying to move here. And so what I'm going to do is then look to see what is acting on my box. Well, the box is definitely being pulled on to the right with a cord that I can see. So I'm going to call that force tension. to the right. I also know that the box is on the earth, so there is a gravitational force on that box, and there's also a surface that it's sitting on, and that surface is pushing up on it, and I'll call that the normal force because it's perpendicular to the surface. And then because these two surfaces are rough and not perfectly smooth like ice or something like that, then there would be a force, friction, kinetic, and I know it's kinetic because it's moving at a constant speed, and a constant velocity or constant speed means that the acceleration is zero, and a zero acceleration would mean that the net force is zero, or we're in equilibrium. So next step is to then sum the forces in the x and y direction. So let's do that now. If I sum the forces in the x direction, they should be equal to zero because the system is in equilibrium. There's a tension force to the right, a friction force while it's moving, so it's kinetic, and that will equal zero. When I sum the forces in the y direction, they should also be balanced. The system is in equilibrium. There's a force normal up, a force weight down, and they equal to zero. Now again, I'm looking for the force I need to pull on the rope, so I'm looking for that tension force. Again, doing the algebra steps here, I can write that my tension force should be equal to the force of friction, kinetic, and similarly, my normal force is equal to the weight. Now be careful because the normal force is not always equal to the weight. We'll look at some of those problems soon. So I know from our lab that the force of friction depends on the coefficient of friction and the normal force. So making that substitution, force tension is equal to mu kinetic times normal, and our normal force then would be equal to the weight, which is equal to mg. Again, be careful, the normal force is not always equal to the weight. This is a special case here. Sometimes the normal force is equal to other forces. Just depends on what the forces in the y direction are. Now, I can make a final substitution step where I take my tension force and my mu kinetic, and then instead of normal, I'm going to substitute mg in for the normal force. So then that would be times mg. And so I'm going to have that the tension force would be equal to 0.1. That was my coefficient of kinetic friction that was given in the problem, times the mass, which is 20, times g, which is 10. So that would give us 20 newtons. So the force needed to keep the box going at a constant speed is 20 newtons. To keep the box going at a constant speed. So if we go back up to our original question here, we need a force tension equal to 20 newtons. This is the force needed to keep it moving at a constant speed.